My name is Alex Roush, and I am honored to be here to start this lecture series on single variable calculus. I know that all of you are here for differing reasons, and I hope that you get something out of every single one of my lectures. So to start out with, I want to explain what this lecture series is and is not. So here's essentially what I want you to get out of this lecture series. I want you to understand that I'm going to try to explore calculus through three branches. Okay, a conceptual branch, a conceptual or intuitive branch, an analytical branch, sometimes called the mathematical side of things, where we actually look at formulas, and a graphical approach. Some colleges call this calculus and analytic geometry, so it's also the geometric approach. Okay, so what that essentially means is after every single one of my lectures, if you don't feel like I explained the concept to you, then I essentially failed you. Because most teachers in high school, they give you a bunch of complicated formulas of derivatives and integrals that scare students off, and they feel like it's more memorization than anything. So essentially what this is not going to be some sort of a formula class, where I go through a bunch of examples and I essentially teach you only how to do the problems that are going to show up on tests and exams. Okay, so I hope that I actually explain the concepts of calculus. So to start out with, I want to start out with the history of calculus. It's going to be very brief, hopefully, less than 2 minutes. And calculus essentially started, that would be the late 17th century with two individuals that independently discovered the principles of calculus, Sir Isaac Newton and Wilhelm Gottfried Leibniz. And essentially what they discovered were two problems that I hope to answer throughout this course. But I just want to introduce you to these two problems, and hopefully we'll explore a little bit more about those problems in the coming weeks. So the first problem is called the tangent line problem. The tangent line problem. And it says the following. Let's say that I'm given some sort of a graph. Okay, and I have a function, the arbitrary function, we'll just call it f of x. And the tangent line problem says the following. If I pick some point C right here, can you find the slope at that point on that curve? Okay, so can you somehow get around to find the slope of that line that I can draw tangent to that curve? Okay, so right away your answer should be no. If it isn't no, then you shouldn't be watching this course. But if it is, then you can't find the slope at one point, right? Slope by definition is the change in y over the change in x, and it requires 2 points in order to find that. Okay, so the answer to this problem, as we're going to come to find, is known as the derivative. Okay, it's the derivative, and it's sometimes noted d dx. So if you've seen that in the front of calculus textbooks and that scared you away, it should not scare you away. It's just d dx. It's the derivative, and it's essentially slope. So I want to go through 3 examples of where this would be applicable in life. So I'm all about application, okay? So the first application could be something called profit maximization. So as a businessman or businesswoman, you could be given something called a utility curve. And that's essentially a mathematical map of all your preferences, right? So if I'm dealing with like pizza and movies, which combination of pizza and movies will give me the highest happiness, essentially? Okay, so a derivative allows me to find the combination of items such that my happiness or utility is maximized, my profit's maximized. You can do cost minimization. That also falls under the derivative. Okay, another application in physics is something called the centripetal force. So what the centripetal force essentially is if I'm given some sort of a circular path, okay, along here, I can measure the force along this path by the formula v squared over r, where r represents the radius of that circular path, and v represents the instantaneous change in position. So essentially, how am I changing my position? How fast am I going at this exact instant in time? So anytime you ask yourself, well, this is a rate of change problem, or this is an exact situation where I want to know exactly what's going on at this instant in time, it's probably going to be answered with the derivative. And my final application is something called an equivalence point. So if you know what a titration is, essentially you add something called a titrant, a solution, to bring it to an equivalence point, and it has a measurable color change with a certain pH value. And you measure the concentration or molarity of that solution. So if I'm given some sort of a graph like this, where the amount of titrant changes, and I'm looking at the pH, what an equivalence point would be is essentially this guy would go up until I would have something like this guy. We track that back to a certain pH level, and we'd call that the equivalence point. Okay, so that uses the second derivative, because that's actually something called an inflection point. More on that to come. But this is essentially the whole root of what we're going to be doing the first half of this lecture series, is dealing with how to find the slope at a point on a curve. That's what the derivative represents. The other fundamental problem in calculus deals with something called the area problem. The area problem. And here's the area problem. Suppose I'm given kind of the same setup. I'm given some sort of a function. And I'm defining it definitively from A to B. So I say this point to this point. Okay. All the area problem asks us to do is to evaluate the area under that curve. So this region right here. Okay, intuitively you should say, well, I don't know how to do that. I know how to find the area of things like triangles and rectangles and circles. And obviously that's a curve, right? I don't understand how to find the area under something that's not really one of those simple figures that I described. So the answer to this problem is known as the integral. Okay, so the symbol for an integral looks like a curly S. It's actually the Latin S. Okay, and some applications of the integral, well, you can actually find some volumes with some pretty obscure shapes. So just to kind of give you an example, let's say that I have a function like this, and I wanted to find the volume of this guy. Okay, well, you can use integrals to solve that. Okay. Another application of the area problem, or the integral, is something called convergence. Convergence of infinite sums. So maybe in your geometry class, or algebra class, you worked with something called the geometric series. Okay, but these series are essentially a series of terms that are added together to either go to infinity or to converge to some finite value. Okay, so we can use the integral because it's the idea of adding up a bunch of region in space. Okay, and the last application that I want to talk about, and of course there's several more that I'm listing, but I don't have time to go through all of them, probability distributions. When would you want to find the area under a curve? Well, when the area under the curve represents the probability that an event's going to happen. So it's actually called the Gaussian normal distribution. It looks like a little bell curve like that. I'm going to look it up. It's the Gaussian normal distribution. Okay, and essentially wherever I'm at, up to a certain point, the area under this entire curve is defined to be 1. So if I look at the area under this part, that represents the probability that an event is going to occur. So those are some applications of the tangent line problem and the area problem. Both are fundamental to calculus, and both have the same exact answer that I'm about to start this lecture series off with, and that is the idea of a limit. So let's talk about what a limit is. So suppose that I'm given some sort of a function to start out with. It really doesn't matter what this function is, but just to be perverse, I'll pick tangent of x. I'll pick tangent of x minus 1. So I'll go ahead and graph that for you. Okay, if you don't know what tangent of x looks like, graph it on Desmos or your graphing calculator or whatever, I don't care. But you should know that it has a y-intercept of -1, it has a vertical asymptote of pi over 2 and negative pi over 2. So what that looks like is at pi over 2, negative pi over 2, maybe I should be doing this in a different color. we have vertical asymptotes. And essentially what that function is doing is it's starting here and it's going to project upward. It's never going to hit pi over 2. It's going to go the other way and do the exact same thing. That's what the graph of tangent of x minus 1 looks like. So, and it keeps doing this, right? It keeps repeating this exact same behavior, right? So we're going to have a point where it does the exact same thing. Okay, so my question is, number 1, what happens at x equals 0? What does the function do? What's the behavior of the function at x equals 0? And my second question is, well, what happens around x equals 0? So take a few seconds, think about those questions. We'll come back and answer them. Welcome back. I'm sure every single one of you hit the pause button. Yeah, right. So what happens at x equals 0? Well, at x equals 0, my function starts out at -1, right? That's what it's defined to be. F of 0 is -1. If you plug that in, tangent of 0 is 0. 0 minus 1 gets me an f of x of -1. What happens around x equals 0? Well, nothing unusual, right? You just expect it to be continuous up to -pi/2 and pi/2, which are asymptotes. But around that, like locally speaking, this is a continuous function. I don't have to pick up my pencil as I'm drawing this curve. Okay, so what happens around x equals 0? I'm just going to write nothing special. It behaves normally. Okay? So hopefully that's not unusual, but if I ask a slightly different question, let's take a completely different function. It's going to be completely different, right? We'll call this function g of x. Let's say g of x equals the following. Tangent of x minus 1 times x over x. Okay, so I'm just going to go ahead and be nice and draw the function out again. The function's going to look like this. So here's -pi/2, here's +pi/2, that's -1. Function's going to look like this. It's going to look like this. That's what the function of g of x looks like. All right, so I'm going to ask the exact same questions as I did before. So what happens at x equals 0 and what happens around? So now take a few seconds and actually think about this question. Let me know what you think. All right, what happens at x equals 0 is I can't plug in 0 to this function. I don't get anything substantial, right? Because tangent of 0 minus 1 is -1, but I have this 0, right? 0 times anything is 0. I have 0 on the numerator. I'm dividing by 0 on the denominator. I get 0 divided by 0. So technically g of 0 is that mess. Well, what is that mess? I can't answer that question quite yet. Just know that it doesn't have a point. It's literally not defined at x equals 0. So it's not defined. But I'm going to ask a very useful question. What happens around x equals 0? Well, around x equals 0, it behaves perfectly. In fact, this function, compared with this function, they're the exact same except at this one point. I just took that point out. It's called a removable point discontinuity because it's a single point, and I chose to take that out of my function. If I chose to take it out of my function, if I forced you at gunpoint to tell me what do you think is going to happen to the function whenever I plug in x equals 0, you're going to say, well, it looks like it's going towards -1. And there are ways of analytically doing this, or I guess graphically doing it, with tables that you can actually approximate. You can plug in like g of 0.000001 and g of like -0.00000, or I guess -0.99999, or sorry, we're looking at x equals 0. So yeah, if I plug in this guy into my calculator, I'm going to get a value that's really, really close to -1. Probably like negative 0.99999, etc. But it's never going to be exactly equal to -1. And that's the idea of a limit. A limit is what your function is doing, the behavior of the function around the point that you're trying to figure out. All right? So essentially, by answering part B for both questions and for any question that you try to do, you're essentially answering the question of a limit. Okay, so let's define a limit. And I'm going to tell you up front that although this is going to be really scary, this is actually the informal definition of the limit. And next lecture, I'm going to get way more formal with it. So if this scares you, then you haven't seen anything yet. So let's go ahead and define a limit. All right, so by notation, if I'm saying that the limit of something exists, I'm going to say that the limit as x approaches some value c of a function is equal to, we'll call it L. So I'm going to draw a picture just so we understand what that means. So suppose I have some sort of a function. Doesn't really matter if that function's doing it. Okay, so that's my function. And I want to know what happens at this point right here. Do it a different color. I want to know what happens at this value of c. And the function may or may not be defined there. It doesn't matter with a limit. I'm going to show you why in just a second. So what we're essentially saying is, as my x value goes towards c, my function goes towards a specific value. So another way of saying that is, let's imagine that c has kind of like a range of values around it. Okay, we'll call this guy x sub L, meaning it's to the left, and this guy x sub R, meaning it's to the right of the point that we actually care about. We care about what f of c equals. Okay, so x sub L and x sub R for the left and the right. Well, those are going to correspond naturally to y values, where this guy is f of x sub L. This guy is f of x sub R. And when I plug in c exactly, here it's defined, so I can track this back and say this guy is f of c. And I know it's getting really clustered, but hopefully you see that what I'm trying to get you to see is, no pun intended, there's a c value right here. Around c, there's a range of values. So essentially what I'm saying is, if x sub L converges and goes in this direction, how is that going to affect my f of x sub L? Well, if I track it back here, and as I get closer, this guy is going to move upwards. Right? And as x sub R converges and goes to the left, okay, if I track it back to f of x sub R, that's going to correspond to this guy moving downwards. So all a limit is saying is that if I go around c and I converge on the value of c, if I pinch this inward, that's going to pinch the y value, the range inward, and I'm going to converge on an actual value that we've defined to be L. So just to go over what this notation means, I'm saying that the limit, as my x value, any x value converges on c, corresponding to this function, is equal to L. Because f of c is equal to L. Right? So if my function is continuous, so if f of x is continuous, and I define continuity very messily, continuous. So basically, a continuous function is defined as one such that you can draw the entire function without picking up your pencil. This limit is equal to the same thing you would get if I just plug in c. It's equal to f of c, if it's continuous. If it is defined at this point, then if I plug this point into my function, that's what the limit equals. Okay, so continuous functions can be functions like polynomials, nice trig functions, sine, cosine, tangent up to an extent, right? Why tangent up to an extent? Well, if I want to know what happens around pi over 2, I have no idea, right? It goes upward to positive infinity in one direction and negative infinity up to another direction. So I'm going to go over that in just a second. So this is the informal definition of a limit. As these guys converge on C, these guys converge on f of C if it's continuous, or it converges on L. Either way, it's the idea of a limit. All right, so what happens when a function isn't continuous, right? There are stipulations. So what if f of x is not continuous? Well, I've narrowed it down to 3 possibilities. Number 1, we have what we discussed before with the tangent graph. There's a point discontinuity. Continuity. Okay, so a point discontinuity is essentially whenever the function isn't defined at a specific point, let's call it C. So that's where f of C isn't explicitly defined. So what that means for the limit, we essentially have the function, but the point discontinuity would just be multiplying and dividing by the same thing. Okay? You would get 0 divided by 0 if you plugged in C. So this idea of f of C, plug this into your function, then you'd get C minus C divided by C minus C. That's 0 divided by 0, which is not defined. It's just a point that doesn't exist on the function. Now you may be wondering, well, if these guys are the same and it's a function, couldn't I just cancel them out, right? Couldn't I do one of these guys? Couldn't I cross them out? The answer is yes, but only if you're dealing with a limit. Because with the idea of a limit, I don't care what actually happens at x equals c. Right? I don't care what happens at this point. I care what happens around. And around that point, it looks like it's going towards a c value. But with a limit, you have to make the distinction that I don't actually care what happens at the exact point. It's very important to understand that. Right? So that's a point discontinuity. And I'll just draw a picture just to make sure we understand the idea. So here's my picture. I have a function that's defined everywhere but a certain point, and we'll call that point C. F of C is not defined, but with the idea of a limit, I know that it's approaching this value. Right? So an example of a function like this could be something like, well, if I wanted to find the limit as x approached 2 of some function, let's say x times x minus 2 over x minus 2. Right? Because if I plug in 2, that's 0 over 0, I don't know what that is. And in actuality, what you're going to find is if I cancel those out and I plug in 2, it looks like the function is approaching 2. And you're actually going to get a line that's defined everywhere except at 2, there's a hole in the middle. But since the function does look like x, if I plug in 2, the limit would be 2. Okay, so I hope that becomes clear as we move towards an example. The second type of discontinuity would be a jump discontinuity. So with a point discontinuity, you can solve that using calculus. Jump discontinuity, you can't. There's nothing you can do. And the reason for that, I'll explain. So let's say I'm given some x equals c value, and I have a range of y values this time. Okay, we'll call that a to b on the y-axis. So let me draw a picture before I even say any more. So what a jump discontinuity would look like is I would have a function. I would start out all the way over here, it's defined here, and then it just jumps up a range of y values. That's what I was talking about with the whole a to b. So it starts from a, jumps up to b, and just decides to continue. Now this is still technically a function. Why is it a function? Because it passes the vertical line test. At everywhere along this function, the vertical line only touches the function at most 1 point. Because right here, it's not defined here, but it is defined here. So here it would just be 1 point, this point, whatever f of a is equal to. But as far as this goes, you can obviously see that if I have a c value right here, and I'm trying to approach it from different angles, there is no chance I'm going to converge on a single value. Look at the infinite number of points right here that I could choose from. So if I plug c into my function, I have no idea what that's going to be. In fact, you can't even define a function simply in terms of a jump discontinuity. You'd have to break it up into a piecewise function. Another way of thinking about it is whenever I talked about the left and the right-handed side limits, so this would be x sub r and x sub l, very informally. X sub r is doing something different than x sub l. They're approaching different values, right? This guy's approaching b, and this guy's approaching a. They're approaching different values, and thus the limit definitely does not exist. So, given some x equals c value and a range of y values that it essentially skips, f of c is either a or b. If I plug in my c value, it's either going to be this guy or this guy. In this case, I chose to shade in this guy, but I could have just as easily drawn an open circle and closed that guy up, and then it would be b. So I'm essentially skipping all of that. So an example of a jump discontinuity would just be a piecewise function. So if you don't know what a piecewise function looks like, it's essentially saying that I'm defining a function and I'm making it equal to one function, and then I define a condition, and I make it equal to something else given another condition. Okay, so here the limit cannot be taken. Right? So point discontinuity, the limit can be taken. I haven't really explained how yet, but I think you can see right from here, if you just factor that out and cancel it, hopefully it makes sense that it's just a point. And that with the tangent graphs that I showed you earlier, right, these two guys, they're the same function, except one of them has a point discontinuity. So if I factor out what's causing the point discontinuity and I just get rid of it, they're almost the same exact function, and if I plug in the value at x equals 0, I'm going to get a value that right here would be the limit, and right here would be the actual function value. So I hope that's at least kind of clear right now, but I'll go over it in the example. In a jump discontinuity, there's no chance you can take the limit of it because it skips a whole range of y values. There's an infinite number of points that the limit could take on, but essentially it's either going to be a or b, depending on where you're approaching from, if you're approaching from the right or from the left. Okay, the last type of discontinuity is technically present in the tangent of x function. It's an asymptote, and in fancy math talk we call that an infinite discontinuity. All right. Hardest thing I've had to do all day was spell the word discontinuity. All right, infinite discontinuity. So that's essentially whenever, so x equals c is an asymptote and cannot be removed from the limit. So we call this a non-removable discontinuity. A point discontinuity is a removable one. I mentioned before, because I can take that point and either take it away or put it back. Like I had that capability. How do you take an entire line? How do you take an entire field of points and just take all those out or put them back in? So my picture would essentially just look like this. I'd have some sort of an asymptote that would happen to be at the value x equals c. Okay, and I have a function doing that from one side. I have a function continuing from the other side. Right? It's doing different things. If I approach it from the left, it's going off to positive infinity. If I'm approaching from the right, it's going off to negative infinity. Okay, so here in fancy limit talk, we would say the limit as x approaches c of this function value, well, a point discontinuity would say, I'm going to multiply and divide by the same thing so that you can sneakily cancel that out. Here, I'm just going to divide by the discontinuity. I'm going to divide by x minus c, and if I plug that in, I get 0 in the denominator. That is a big hint that you're dealing with an asymptote, and you can't take the limit of this. Okay, so here, I'm going towards positive infinity. Here, I'm going towards negative infinity. I couldn't imagine a situation where these guys would be more different. So I have no idea what the limit would be if you're approaching c. If you're approaching any value aside from c, right? If you're approaching, let's say this guy, well, that's pretty obvious. You just plug that into your function. If I took this point out and I asked you to find the limit there, well, you'd still plug that point back into the function and just pretend it was there, because that's a removable discontinuity. It's a point discontinuity, right? All right, I promised an example. Let's go ahead and go through that. So, example. So I want you to find the following. Find the following limits pertaining to the function. X to the fourth plus 8x all over x cubed plus 5x squared plus 6x. So in your mind, you should be thinking, well, can I factor that? Why would I want to factor that? So if I have common terms and I'm going to cancel that out, those would be point discontinuities. I'll go ahead and tell you what I want you to find. So I want you to find the limit as x approaches 1 of the function, the limit as x approaches 0 of the function, the limit as x approaches -2 of the function, and the limit as x approaches -3 of the function. So I would pause the video, spend a few minutes trying to figure this out on your own, and then come back and I will go through the problem with you. Alright, so like I mentioned with the whole factoring situation, let's go and just factor this to make this easier on our lives. On the numerator, I can factor an x out. So if I factor 1x out, I get x cubed plus 8. On the denominator, I can still factor out an x. I would get x squared plus 5x plus 6. And then this can actually be factored further. So on the numerator, you might not recognize it, but that's actually a sum of 2 cubes. And if you don't remember what that is, I'll be a baby and I'll just go ahead and tell you. The formula looks like this. Okay, and if it was the difference of 2 cubes, it'd be the same thing, only a minus b and plus ab. Okay. Those are formulas that don't pop up very often, but when they do, you're going to get really frustrated if you haven't memorized it yet. So I would just go ahead and memorize them. Okay, so if you factor that guy, this would be x plus 2, because 8 is 2 cubed, times x squared, running out of room, x squared plus, let's see, that'd be 2x, running out of room. Let me do it over here. So this guy would be x plus 2 times the quantity x squared minus 2x plus 4. Now on the bottom, I can factor the denominator yet again with the whole x squared plus 5x plus 6. So what would that be? That would be x plus 3 times x plus 2. So now immediately, those functions are identical. All I did was factor them. Okay, so hopefully when solving these limit problems, the first thing you do is just automatically see if you can factor some stuff. All right, so let's look at 1. The first thing you should always do is imagine that this is an actual graph of a function, and if I plug in 1, sometimes what happens around 1, which is what a limit is asking, what's happening around x equals 1, sometimes that question is the same thing as what's happening at x equals 1, because the function's defined there. So you should always check and just go ahead and plug that into the function mentally and see if there are any discontinuities. And it just so happens that there aren't any. So in reality, what you would do for this question is just plug in f of 1. And when you do that, I'll leave you to do the calculations yourself, but that's 9/12, which is 3/4. Here, if I plug in 0 to the function, right, I get 0 over 0. That's definitely a problem, but I know that if I look at the factored form of this, I actually have an x divided by an x, and that's what's causing me my trifold. So if I plug in 0, this is the part of the function that would be undefined. So if I just kind of discretely take this guy and just remove it, and just look at what the function's doing over here, I have the same function, completely the same behavior, just it's not defined at x equals 0, right? So here, if I plug in 0 to this function, that would be the correct answer of what the limit is doing. Because again, just like with this guy, same function, but if I cancel these guys out officially now, so I'll officially cancel these guys out, bam, bam, I just get f of x, and then I can plug in c. It's going to be the same exact value because the function has the same behavior. It's just not defined at that one point. So the answer to this question, what is the function doing as x approaches 0, is the same question, or the same answer as to what the function is doing at x equals 0 of this function. So if I take 0 and plug that in, do a bunch of algebra, you'll find that the answer is 4/3. So I'll go ahead and denote that. Let's call g of x this function, all I did was cancel x and x, right? This is my function f of x. I'm defining another function that's the exact same everywhere except at x equals 0. But limits don't care what happens at x equals 0. They care about what happened around x equals 0. So therefore, with this function, I don't have any problems. If I plug in g of 0, I'd get 4/3. Here, what happens as x approaches -2, well, that's a discontinuity. Is it a point discontinuity? Yes, because I have an x plus 2 term in both the numerator and denominator that I can choose to cancel. Now, here's a question. Would it be a good idea to cancel that x over x and x plus 2 over x plus 2? And the answer is no, it's not a good idea, but it actually doesn't matter, right? Because, excuse me, if I have x approach -2 and I plug that in, I'd get -2 divided by -2, and those would cancel out. But it's the wrong idea to assume that you can just cancel out whatever you want. That's not what a limit is. So technically, in order to answer this question, I would define a new function. Let's call it h of x. And h of x is going to be the exact same thing as this function. I'm just going to cancel these guys. I'm going to cancel what's causing me my problems. And if I plug in -2, that's what's going to go to 0. So I'm going to define this as x times x squared minus 2x plus 4 divided by x times x plus 3. Okay, so then I want to find h of -2, and I work this out to be -12. Okay, lastly, what happens as x approaches -3? Well, here I don't have any problems in the numerator, but I do have a problem in the denominator, right? I have a 0 in the denominator, and if you remember from our talk about infinite discontinuities, that's essentially whenever I plug this in and I get 0 on the denominator. If you can't cancel it out with something on the numerator, that means you're dividing by 0 alone, and that's going to have an asymptote. Therefore, this limit specifically, because plugging this in would result on, it would result in 0 on the denominator, but not in the numerator, this limit does not exist, D and E. All right? All right. A few more topics I want to go through for today. So this limit idea. So another way of phrasing whether a limit exists or not is by saying the following. If the limit as x approaches c from the left-hand side, that's what that minus means, from the left-hand side, equals the limit as x approaches c from the right-hand side. Okay? So somewhere, whenever I first mentioned limits, I mentioned these guys and I said, well, from the left and the right, they seem to be converging on a value, but let's see. Somewhere where I had a jump discontinuity, for example, they're approaching different values. So the limit as x approaches c from the left-hand side, with that little minus as a superscript on the c, is different. It's a, and from the right, with that plus superscript, is equal to b. So this would be applicable to jump discontinuities. Yeah, a limit exists if the left-sided limit equals the right-handed limit. Okay. So do another example. Okay, so I'm asking you to find all values of b, the constant b, for which the function h of x is continuous. And you can use this idea of the left and the right-handed side, or the left and the right-sided limits being equal. You can use that to kind of justify continuity. I won't go into how, but you can figure it out. So I'm going to say that h of x equals the piecewise function. It equals 3x. This function is equal to 3x, provided that x is less than or equal to 1. And it equals the quantity b squared, provided x is greater than 1. So notice that this is a constant, but it's also a variable. I can change this and make it so that this function is continuous. So a lot of times I feel like the best way to approach a problem like this is to actually graph it. So if I graph this problem out, the function is equal to 3x, provided that x is less than or equal to 1. So here's everything I'm concerned with right now. In this region of my graph, my function is 3x. So it has a y-intercept of 0. It goes up 3, over 1, down 3, to the left 1. It's going to look like that. So from negative infinity all the way up to x equals 1, that's my function. Now, from x equals 1 beyond, it's equal to b squared. I don't know what b squared is. So I know that here, it's b squared. But I do know that since this is a constant, I have a function equal to a constant. If I had y equal to 4 or y equal to 3, that's a horizontal line, isn't it? So I'm essentially saying, or it's a horizontal line. Where do I need to position that horizontal line to make this graph continuous? To make it so that right from here, I don't have to pick up my pencil. So intuitively, you should kind of understand that it needs to start right here. So if I plug in 1 to my function b squared, it should be equal to whatever this value is for y, which happens to be 3, right? If I take this 1 and I plug it into the function 3, I get h of x equal to 3. So my b should start, or my function b squared should start at 3. Therefore, b squared as a function needs to start at 3, and b can be plus or minus the square root of 3. Okay, now I want to justify this using the idea of limits of these left and right-sided limits. So I'm going to say the following. I'm going to say that this change in the function happens at x equals 1. We'll call that a breakpoint. So the limit as x approaches 1 from the left-hand side of the function. Now, what is the function as I'm approaching 1 from the left-handed side? Well, that's this function, isn't it? It's 3x. That has to equal the limit as x approaches 1 from the positive side of the other function, of b squared. And it's always worth plugging it in because these are continuous functions. In and of themselves, they're continuous. We want to make the combination of those functions continuous. So we want to make sure these limits equal from the left and the right-handed side. So the limit as x approaches 1 from the left-handed side of 3x is 3. Here I plug in 1. Well, it doesn't change anything, right? It's not a function of x, regardless of any x. So if my b were this function, regardless of any x I pick, I'm going to get the same limit value. I'm going to get b squared. Okay, so that's how you can solve it in a little bit more of an algebraic way. Still get plus or minus the square root of 3. And if you plug that in, you'd get 3 as your function, which matches up and makes this continuous. All right, so the last topic I want to cover for today is one that a lot of calc students love so much, right? Especially with this idea of a limit. You'll love it too. When are you allowed to write d and e? That's like a calc student's favorite combination of letters, right? D and E does not exist. I don't have to do anything. But you should know when you can't do anything and when you can do anything so you don't miss points. So when can you write this d and E? Well, some possibilities should be jumping in your mind. Number 1, jump discontinuities. And for that matter, infinite discontinuities. Right? If it's a jump discontinuity, then we're going over here, and then we're jumping upwards, right? That limit at that point doesn't exist. But an infinite discontinuity also doesn't exist because there's a big fat asymptote right there. And even if they approach the same thing, they never ever touch that line, right? So I think I defined an example function as negative x provided that x is less than or equal to 0 and x if it's greater than 0. So really quick, what does that look like? Well, it's negative x right here, it's positive x right here. Or sorry, no. That's not what negative x looks like. There we go. So it's the function negative x. If we're approaching from negative infinity up to 0, 0 on, it's a positive x, and that's how an absolute value function is defined. Right? You can also write d and e if you know that it's an infinite oscillation. So I'm going to describe that really quickly. You're not going to see this very often. When you do, you're just going to punch in your graphing calculator anyway. But if I had a function like, let's see, g of x equals, I don't know, negative cosine of 1 over x minus 2 squared. If you type that into Desmos or whatever, you're going to get a graph at x equals 2 that's going to do something like this. You're gonna have some sort of a periodic motion right here, down and up and down and up and down and up and down. And it's going to be crazy, right? I'm not going to be able to tell over here what's happening at x equals 2 because it changes. It oscillates. It goes up and down and up and down. Okay, a sine function does that, but it does it periodically, right? You can tell whenever a function is going to be pi over 2. Like if I plug in pi over 2, you can tell what that value is going to be. With a function like this, it goes faster and faster and faster, and it oscillates more and more up to the point you want to take the limit of. All right, finally, you can write d and e with one-sided limits. So I doubt you're going to see an example of this, but essentially you have a limited range. So let's say I defined, I don't know, y equals 1 over x for provided x is greater than or equal to 2. And I wanted to know the limit as x approached 2. So what that would be is essentially, well, 1 over x kind of looks like that. And if I take this point 2 right here, and I define the function only from here on, and I want to find the limit as x approaches 2, you can't do that, right? Because there's no left-handed limit. There's no left-sided limit. I can't approach from the left because my function's not defined there. So if you run into a situation like that, the limit would also be a DNE in that case as well. All right, so in your calculus textbook, or whatever you're going to use, you're probably going to see something like this, and it's really ugly and messy, and I really don't feel like going through those properties of limits. But I want to say a few words about these to close us off. So first, the following information is given provided that b and k are constants, not functions relying on a single variable. Okay, we're going to define the limit as x approaches c of a function f to be L, and the limit as x approaches c of g of x to be m. And I really, really sincerely hope that all of these are intuitive. And if they aren't intuitive, then take this as a function and actually graph the graph of b. We did an example of this, the second example. If you graph b, that's a horizontal line. Doesn't matter where my x is going to be, the y value is going to be the same thing. All right. And these values just say, well, the limit as x approaches c of f of x is L, that's just going to be KL. That's L plus or minus m. So they really mirror. And this guy, this is provided that the limit as x approaches c of g of x does not equal 0. Right? Because if it did, then we'd be dividing by 0. So hopefully that's all intuitive and you understand that. In the next section, we're actually going to prove some of these properties using the formal definition of a limit. But before I go, I want to define 2 very special limits that I want you to memorize for now, and then I will explain and prove the concepts behind these 2 limits in the next lecture. So they're both trig related. So the limit as x approaches 0 of sine of x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine of x over x is 0. When I took calculus in high school, a very smart individual pointed out that sine has an I in it, and a 1 kind of looks like an I, and cosine has an O in it, and that kind of looks like a 0. If that helps you remember it, then go for it. Otherwise, I'm going to prove these in the next section. Thank you all for watching this. I hope that you got something out of it. We talked a little bit about limits, their properties, and in the next section I'm going to go more in depth and talk about some of the things that you probably wouldn't cover in a first-year calculus course, but I do think that they are very important. So again, thank you very much for watching, and I hope to see you in the next lecture.